Hello, Plockton High School. Are you ready? Let's go.
It's time for Maths with Mr. Thomas.
Chapter 12, lesson number 7, looking at trig, identities. Now, Moivre's theorem that we looked at a couple of lessons ago provides a connection between expressions of the form cos theta and sin theta to the power of n. As you can see here, if you've got your complex number in polar form, r bracket cos theta plus I sin theta, if you want to work out the power of that, so if it's to the power of n, you know all that you do is you multiply your argument by n. So De Moivre's theorem provides a connection between the cos term and the sin term to the power of n and your cos n theta and sin n theta. What you can do is you can use De Moivre's theorem as long as a blast from the past binomial theorem to produce trigonometric identities. So let's do that with a few examples. So example 1, expand cos theta plus I sin theta cubed by the binomial theorem, writing your answer in the form of a plus ib, where a and b are trigonometric expressions, and b write another expression for cos theta plus I sin theta brackets cubed using De Moivre's theorem, and hence show that cos 3 theta equals cos cubed theta, take away 3 sin cubed theta cos theta. And once you've done that, write an equivalent expression for sin 3 theta. So for part A, expand the cos theta plus I sin theta in brackets cubed using the binomial theorem and writing our answer in that form with the real part and the imaginary part. So A plus IB. Well, to do that, what we really want to do is we're wanting to expand it. So we want to use the binomial theorem on the cos theta plus I sin theta cubed. We know really what we've got from lesson 5.3 is if we've got something plus something to the power of n, well, you're going to have nr bracket x to the power of n minus r and then y to the power of r. So here, because it's to the power of 3, we know we would have to work out your 3, 0, then 3, 1, then 3, 2, then 3, 3. So we're wanting the sum of 3r, and then this here will be the x part, so it'll be cos theta to the power of 3 take away r, and then this here will be the y part, so it'll be I sin theta to the power of r. We're wanting the sum of that, so with all the terms we're going to have a 3 0, then 3 1, then 3 2, then 3 3. So let's write that. So the binomial coefficients, we've got 3 0, 3 1, we've got a 3 2, and we have a 3 3. We know this x part here, the bit that's first, is cos theta, so we're going to have our cos theta going from the power of 3 on to 2 on to 1 all the way down to 0. So we'd have cos theta to the power of 0. With the other part, with the I sin theta, we're going to have that to the power of 0, then we'll have that to the power of 1, then we'll have that to the power of 2, and then we'll have that to the power of 3. So, binomial coefficients, 3, 0, 3, 1, 3, 2, 3, 3. And the bit that's first, cos theta, you've got that from the power 3, then 2, then 1, then 0. And the other part, you're going to increase the powers, so from the power of 0 to 1 to 2 to 3. Working that out well for the 3, 0, 3, 1, 3, 2, and 3, 3. Using Pascal's triangle, well, you're going to start off with your little triangle of 1, so you'd have 1, 1, 1. For the next row, you're going to have 1, and then add these two to get 2, and then you're going to finish with a 1. For the next row, with the third, which is what we're wanting, you're going to have 1, add these two to get 3, add these two to get 3, and then finally finish off with a 1. So for 3, 0, 3, 1, 3, 2, and 3, 3, you're going to have 1, 3, 3, 1. So you're going to have 1 times the cos cubed theta. Because this is to the power of 0, that will really just disappear. You multiply by 1, leaving you with the cos cubed theta. This here, 3, 1 is 3, so that's going to be 3 times. This is cos squared theta, and I sin theta is just to the power of 1, so it'll be I sin theta. 3, 2 is also 3, so that'll be 3 times cos theta, multiplied by I sin theta squared, so it'll be the I squared, and then the sin squared theta. And 3, 3 is 1. Cos theta to the power of 0 will disappear, and that'll just be to the power of 1. And we would have our I cubed and the sin theta cubed. Once you've done that, where do you go? Well, the cos cubed theta, you'd leave it as it is. I'm just going to put the I in front, so I'm going to have 3i and sin theta and the cos squared theta. With I squared, what's I squared? -1. Brilliant. So you can replace that with -1 and move it to the front. So you'd have negative and then 3. I'll still get the cos theta and the sine squared theta. And I cubed, well, if you think about that, that's I times I times I. I times I, or I squared, is -1. So we'd have -1 times another I. So -1 times I will give us negative I. And we'll still get this sine cubed theta. What we really want to do is we're wanting to write our answer in the form of a plus ib. So we want to gather the real parts and the imaginary parts. So the real parts here are basically the bits without any i's. So here there's an I in it, so this part's going to be imaginary because there's an imaginary, it's something times I, and this part here will also be imaginary because there's an I. But the other parts, the cos cubed theta, is going to be a real part. So that's a real part, there's no I. This part here as well, there's no I, so it's going to be a real part. So you'd have the cos cubed theta and the take away 3 sine squared theta cos theta. They will be the real parts, and the imaginary parts we're going to have plus I times, and if we take out I as a common factor, for them we'll take out I as a common factor, it leaves us with the 3 sine theta cos squared theta. And if you take out I there, you still have the negative and sine cubed theta. So that's us writing our answer with the real part and the imaginary part there. And that will be it. Part B, write another expression for cos theta plus I sine theta cubed using de Moivre's theorem, and hence show that the cos 3 theta equals this. So this is our answer. This is what we had for part A, but now we're asked to write down another expression for it using de Moivre's theorem. Remember this here. Hello! This part is de Moivre's theorem. So because we've got our polar form and it's to the power of 3, what we'd really have for that is, well, we've got the cos theta plus I sine theta to the power of 3, and we would have, well, the modulus will go to the power of 3, but here you can see the modulus in front of the brackets is just really 1. So you'd have 1 to the power of 3, which is still 1, so really we don't need to write that. So we'd be left with the argument to deal with. So because it's to the power of 3, you just multiply the argument theta by 3. So you'd have cos 3 theta. And then with I sine theta, again multiply this angle, the theta, by 3. So you'd have I sine 3 theta. So using de Moivre's theorem, that's what you get. What we want to do though is write another expression. We've done it, but we're wanting to show that the cos 3 theta equals this. So how do we go about doing that? Well, what you'll notice is in the first answer, or in this answer even, let's go with that first, in this answer the cos 3 theta was the real part. And we know that when we expanded this, this is what we got. But when we expanded it up here, this is what we got. But because there's a real part and imaginary part, and again a real part and imaginary part, really the real parts have to be equal. So we'd have to equate the real part here with the real part from this question, from part A. So if we equate the real parts, we can say then that cos 3 theta, the real part here, equals the cos cubed theta, take away 3 sine squared theta cos theta. So that's us equating the real parts. Once we've done that, what we want to do is we want to write an equivalent expression for sine 3 theta. Well, what you'll notice for sine 3 theta down here, well, the sine 3 theta is what you're multiplying I by. So that there is the imaginary part. And in the first part, well, you know the imaginary part is this. It's the 3 sine theta cos squared theta take away sine cubed theta. And again, because we expanded the same thing, just two different ways, the imaginary part here must be equal to the imaginary part here. So if we compare the imaginary parts, or equate the imaginary parts, we can say that the sine 3 theta must equal that 3 sine theta cos squared theta take away sine cubed theta. You see that? Yes. Woo! Yeah. Example 2, starting with cos 5 theta plus I sine 5 theta equals the cos theta plus I sine theta all to the power of 5. Find identities for cos 5 theta and sine 5 theta in terms of cos and sine. And then hence find an identity for tan 5 theta entirely in terms of tan theta. So we're starting off, if you're wanting to find an identity for sine or cos or tan, what we use is the binomial theorem or de de Moivre's theorem. But you can see here we're already given this part. If we have this complex number in polar form to the power of 5, we know we would use de Moivre's theorem in order to multiply this argument just by 5. But we can see we've already done that. I suppose the modulus, the 1, will go to the power of 5 as well, but that would just be 1 time, so we don't need to write that. So we'd have this cos 5 theta and then I sine 5 theta. So that there is de Moivre's theorem. So that's what that used. But to produce the identity, we need to use de Moivre's theorem as long as binomial theorem. Perfect, the binomial theorem. So now we're going to use the binomial theorem. So if we've got this 5 cos 5 theta plus I sine 5 theta, well, we can say that is equal to the cos theta plus I sine theta all to the power of 5, and we have to expand that. So because we've got really an x plus y to the power of something, this is what you're thinking. So from lesson 5.3, when we're looking at binomial theorem, if we've got something plus something to the power of n, you know really you're going to have the power, well here it's 5, so you're going to have a 5 0, 5 1, 5 2, 5 3, 5 4, 5 5, and you would have your x to the power of 5 take away r. So you'd have your 5 0, then 5 1, 5 2, 5 3, 5 4, 5 5. If you use Pascal's triangle to work them out, well, you would have, if we write that very quickly, you'd have 1 1 1, then 1 2 1, then 1 3 3 1, then 1 4 6 4 1, and then finally you'd have the 1 5 10, 10, 5, and 1. So, you know really the coefficients, you're going to have 1, so I'm not going to bother writing that. Then you're going to have a 5, then we're going to have a 10, then we'll have another 10, then we'll have a 5, and again you'll finish a 1. Not going to bother writing that. We've got this cos theta, and we'd have that to the power of 5, then we would have that to the power of 4, then we'd have it to the power of 3, then to the power of 2, then to the power of 1, and then to the power of 0, so you don't need to write that. With I sine theta, we'd have that to the power of 0, which is why I haven't written it, then we'd have it to the power of 1, then to the power of 2, then to the power of 3, then to the power of 4, and then to the power of 5. Good. Taking that a little further, well, the cos theta all to the power of 5 is just cos theta to the power of 5, so it's going to be cos fifth. And then theta, we've got this 5 times cos theta to the power of 4. I sine theta, we've got the 10, we're just rewriting that. We're squaring the I, well if you have I squared, well we'll deal with that in the next line, just write it as I squared just now. We'd have the sine theta as well, squared. We've got the 10, we're squaring this cos theta. We've got I to the power of 3. We've got the sine theta again to the power of 3. This part, we've got the 5, we've got the cos, we've got I to the power of 4 and the sine to the power of 4. We've got the I to the power of 5 and the sine theta to the power of 5. Dealing with that, well, first part's just going to stay as it is. Next part will stay as it is as well. But here you've got an I squared. What's I squared? -1. Good, so replace I squared with -1. I cubed is going to be I squared times another I. So we'd have -1 times by I. So it gives you -I. I to the power of 4, well that's really I times I times I times I, or in other words, I squared times I squared. I squared is -1, so it's -1 times -1. And that would just give you 1, because 2 negatives make a positive. And with I to the power of 5, you know that's I to the power of 4, multiplied by another I, so it's 1 times I, which will give you I. We have your de Moivre's theorem up here. We've got this cos theta plus I sine theta all to the power of 5 equals that, with your real part and your imaginary part. And we've also just expanded it using the binomial theorem. What we would do next is to get an identity for cos 5 theta. Well, we can see up here that the cos 5 theta is the real part of our complex number. So what we want to do is, if we expand it, no matter which way we expand it, we're going to equate the real parts. So we can say then that the cos 5 theta must equal, well, it's the real part when we expand it one way, which was kind of given in the question, and we expand it using the binomial theorem, that's going to be equal to the real parts of that expansion. So that there is going to be a real part. This part has an I, so you ignore it. This part doesn't, so that's going to be a real part. This part has an I, so it's going to be imaginary. This part here is real, and this part's imaginary. So all you would do is you would equate the cos 5 theta to the real parts in here. And all I'm doing is moving the negative just to the front. So it's take away 10 and then cos cubed sine squared and so on. We also want to get the identity for sine 5 theta. And for sine 5 theta, well, how do you go about doing that? Well, you can see that sine 5 theta is going to be the imaginary part. So for your sine 5 theta, the imaginary part here, equate it to the imaginary part when you expand it. So that there will be an imaginary part because it's got an I. This part here will also be imaginary because it's got an I. And this part here also has an I, so that will be an imaginary part. So all you want to do is you want to equate the imaginary parts and say that this sine 5 theta must equal the 5 cos theta to the power of 4 sine theta, take away 10 cos squared theta, and then I cubed theta plus the sine theta to the power of 5. And that is going to be the identities for the cos 5 theta and the sine 5 theta. For the next part though, it says hence find an identity for tan 5 theta entirely in terms of tan theta. How could we go about doing that? Well, this is the answer that we just had, and because it says hence, we know we're going to be using these answers. So let's go over the page. This is what we just found. We just had the cos 5 theta and we had the sine 5 theta. We know what they're equal to, the real parts and the imaginary parts, but how could we go about getting what tan 5 theta would be equal to? Anybody have any ideas? Perfect! You're right! Tan is equal to sine over cos, which means that tan 5 theta would be equal to sine 5 theta over cos 5 theta. Perfect! You're a genius. So let's do that. So sine 5 theta, we can see that's equal to our answer from part A. So we can say it's equal to all of that. And we're going to be dividing that by cos 5 theta. And cos 5 theta, again, just use your answer from part A. So we get this ugly fraction here. So it's going to be the 5 cos theta to the power of 4 sine theta, blah, 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 divided by that cos theta to the power of 5, take away, and so on. So that's what we've got so far. But we want our answer in terms of tan. We don't want it in terms of sine and cos. So how could we go about doing that? Brilliant. What you can do with that is you can think, right, well, I know that tan is equal to sine over cos. So what we have to do with that is we have to think, right, well, how could you go about writing this all in terms of tan? And the way you can do that is you could look at it and you think, right, well, I need a sine divided by a cos. But if you take this first part here, so you've got 5 cos theta to the power of 4 sine theta. If we divide that by cos, well, that's just going to cancel one cos here with our cos that we add in. If we divide this part by our cos squared, well, that'll just cancel a cos squared with here, 2 of them. So what we have to do is we have to think, right, well, we have to divide it by at least cos theta to the power of 4, because then they would just cancel, but it would still leave us with sine, so we have to multiply it by we have to divide it by another cos theta. So we have to divide it by cos theta to the power of 5. And if you do that, well, you take each of those parts and divide them by cos theta to the power of 5. So divide that part, and that part. What we could also have done is we could have looked over here. We've got a sine theta to the power of 5. So in order to change that to tan, we'd have to divide it by a cos theta to the power of 5. But if we're dividing everything in the top row by cos theta to the power of 5, we have to divide everything in the bottom row as well by cos theta to the power of 5. If we do that then, well, that is going to cancel 4 from the top, 4 from the bottom, so that is going to leave us with 5 sine over cos. This here, up here, we've got our 10, and then we're going to cancel out 2 of the cos's from the top, 2 from the bottom, so it leaves us with 10 sine cubed theta, and then cos cubed theta. And then here, well, that's just going to stay as it is. With the bottom row, the cos 5 theta over cos theta to the power of 5 over cos theta to the power of 5, well, that's just going to become 1 because we're dividing something by itself. Here, 3 of the cos's on top, 3 of them in the bottom will cancel out, leaving us with 10 sine squared theta over cos squared theta. And here, if you cancel out 1 cos theta from the top and another one from the bottom, it would leave us with 5 sine theta to the power of 4 over cos theta to the power of 4. And doing that, well, you've got sine over cos, which is tan. You've got sine cubed over cos cubed, which will be tan cubed. Sine to the power of 5, cos to the power of 5, that would become tan to the power of 5. So really, we would end up with this. So we'd have 5 tan theta, take away 10 tan cubed theta, plus tan to the power of 5 theta, over the 1, take away 10, and that'll be tan squared theta, plus, and then that'll be 5 tan theta to the power of 4. So that will be our answer, and that's an identity for tan 5 theta, all in terms of tan. Woo! Example 3. Given z equals cos theta plus I sine theta, use de Moivre's theorem and the binomial theorem to show that cos 4 theta equals cos theta to the power of 4, take away 6 cos squared theta, sine squared theta plus sine theta to the power of 4, and sine 4 theta equals 4 cos cubed theta sine theta, take away 4 cos theta sine theta cubed. And then B, hence show what tan 4 theta is equal to, prove it's equal to this right hand side, and for C, find algebraically the solutions to the equation tan theta to the power of 4 plus 4 tan cubed theta, take away 6 tan squared theta, take away 4 tan theta plus 1 equals 0 in the interval for theta between 0 and pi over 2. So for part A, given z equals cos theta plus I sine theta, use de Moivre's theorem and the binomial theorem. So starting that off, let's use the binomial theorem. So how do we get the 4 there? Well, we know that in order to go from the cos theta plus I sine theta to having 4, well, we're going to have our polar form all to the power of 4. And if we have our polar form all to the power of 4, well, all we do is we multiply or have the arc modulus to the power of 4, so that's 1 to the power of 4, which just becomes 1, so we're just leaving it as it is. But we'd have the argument, the theta, multiplied by 4, so we'd have this 4 theta, and the I sine 4 theta. Using the binomial theorem then, so for this, once again, you're using Pascal's triangle with 1, 1, 1, and then 1, 2, 1, then 1, 3, 3, 1, and then we'd have 1, 4, 6, 4, 1, so 1, 4, 6, 4, 1. So they would be your binomial coefficients if you swap the binomial coefficients with 4, 0, 4, 1, 4, 2, 4, 3, 4, 4, with 1, 4, 6, 4, 1. So you'd end up with 1 times, and it's going to be the cos theta to the power of 4. So that's going to be the power of 4, and you'd have I sine theta to the power of 0. Plus, then you'd have 4 times, it's going to be cos theta to the power of 3, so the powers are going to be decreasing by 1, but we'd have the I sine theta going to the power of 1. So the powers would start at 0 and then increase. After that, you're going to have plus 6 times. Cos is still going to be decreasing by 1, so we'd have cos squared theta, and the I sine theta, that will be increasing by 1. We then have the 4 times. Cos is still going to be decreasing, I sine theta is still increasing, and finishing off with 1 times, and cos theta will disappear, because that's just going to be to the power of 0, which becomes 1, so we don't need to write it, and you'd have I sine theta to the power of 4. If you start rewriting that, well, what you're going to have is you're going to have the I squared and the sine theta squared as well. You're going to have the I cubed and the sine theta cubed, so it becomes sine cubed theta. I to the power of 4, and the sine theta again to the power of 4. From there, where can you go? Well, if you just tidy that up a bit, you will have your I. That's fine, but here we've got an I squared, and I squared becomes -1, so we can just write that as take away 6, blah, blah, blah. Here you've got an I cubed, which is I times I times I. I times I is I squared, which is -1, times that by another I, it's just -1I. So we can replace I cubed with -1I. So with the -1, just put the negative to the front, and we've still got the I there as well. I to the power of 4 is I times I times I times I, which is I squared times I squared. I squared is -1. If you square that, then you will end up with +1. So you just have plus sine theta to the power of 4. We're wanting to show that cos 4 theta equals that. Well, you can see that cos 4 theta is your real part. So all you want to do is just equate the real parts. This part here is real, it's got no i's. This part here is real, it's got no i's, there's an I there, and this part here is real as well. So if you equate the real parts, you can say that the cos 4 theta would equal just each of the real parts here. And we're asked to show that sine 4 theta equals that. Well, you can see that sine 4 theta is being multiplied by I. It's the coefficient of I, which means it's imaginary. So you would take the imaginary parts here. That's imaginary because it's got an I. This part here is also imaginary because it's got an I. So if you equate the imaginary parts, you'd say that the sine 4 theta would equal, and you're just taking these two parts here. So this part, just don't write down the I because it's just the coefficient of I that we are wanting. So what we're multiplying I by is the 4 cos cubed theta sine theta. And here what we're multiplying I by was the negative 4 cos theta and then sine cubed theta. So we're equating the real parts and the imaginary parts. Part B hence show that tan 4 theta equals that. Using our answer here, well, this is just what we came up with in the first part. This is all we've got. How do we go about showing what tan 4 theta is equal to? Well, it's very similar to that previous example. We know tan is equal to sine over cos, so we know that tan 4 theta will be sine 4 theta over cos 4 theta. So, sine 4 theta was this bit here, just our answer from part A, and we're wanting to divide that by the other answer from part A, so we can say it's going to be this divided by this. But what we're wanting to do is we're wanting to have it so we're showing that it's equal to, remember we were asked to show it's equal to this answer here. So how do we get down to that? Well, we need to put other steps in between. You can see that this part is only written in terms of tan, but we've got it in terms of sine and cos. The quickest way to probably do this is to have a look here and see you've got a number 1. So have a think and think, what do you divide cos theta to the power of 4 by in order to get 1? Well, in order to get 1, you have to divide something by itself. So try dividing that by cos theta to the power of 4, but if you do that, you have to divide everything by the cos theta to the power of 4. So do that. So divide this part, this part, this part, this part, and this part. Divide all 5 parts by cos theta to the power of 4. If you do that, well, that's going to simplify. The first part up here, well, 3 cos's will cancel in the top, 3 from the bottom, so you'd have 4 sine over cos. Here, you'd be able to cancel 1 cos from the top and the bottom, so you'd have 4 sine cubed and then cos cubed. And in the bottom, you divide something by itself, so that goes to 1. Here you can cancel 2 cos's from the top and 2 from the bottom, so you'd have 6 sine squared over cos squared. And then here, because you've got the sine over cos, well, you can just leave that as it is and change that in the next line, because for each one, you've got a sine over cos, which will just swap with tan. So you'd have 4 tan theta take away 4 tan cubed theta over the 1 take away 6 tan squared theta plus tan theta to the power of 4. And that is our answer. Woo! Part C, find algebraically the solutions to the equation tan theta to the power of 4 plus 4 tan cubed theta, take away 6 tan squared theta, take away 4 tan theta plus 1 equals 0, with theta between 0 and pi over 2. How do we go about doing that? Well, we're just going to start off with the equation that they give us. Perfect. Where do we go from here? Well, what we want to do is we want to look back to some of our previous answers. This here was what we had for part B. And a lot of the time, if you get part C, you're wanting to use your previous answers. You can see that every single part of this is somewhere in this equation. We can see it similar to the right-hand side. So what we could do is we could rewrite this in this form, looking at the right-hand side. So we've got a 4 tan theta, so we're going to leave the 4 tan theta. Actually, we're not, because it's negative. Because that's negative, we want to add the 4 tan theta onto both sides, so we'll add that over here as well. With the takeaway 4 tan cubed theta, well, we've got a 4 tan cubed theta, but it's positive, so you know what? Subtract that from both sides. So we're really moving those two over to this side. And in the bottom, we've got a 1, which we've got here, we've got a 1 there. We've got a takeaway 6 tan squared theta, we've got that. And we've got this tan theta to the power of 4, which we've got. So move these two bits just in red, subtract this from both sides, add this to both sides, and we'd end up with that. What we can then do is we can think, right, well, we're wanting to divide this, we're wanting to get that fraction. But imagine putting brackets around this part here to show that you're just multiplying that by 1. So if you divide both sides by the tan theta to the power of 4, take away 6 tan squared theta plus 1, what it will give you is that right-hand side, the 4 tan theta, take away 4 tan cubed theta, and we're dividing it by just all of this in the brackets. But on the other side, what would you be left with? On the left, 1. Perfect. Make sure you're not writing 0 there. Okay, it's just going to be 1 times all of that. So you'll be left with 1. Where do we go from there? Well, as it says here, using the answer from part B, we can see up here that we're told that that fraction is equal to tan 4 theta. So we know then that we've got tan 4 theta equals 1. After that, what do we do? Well, we're wanting to look at the question. We want to solve this for theta between 0 and pi over 2. But we don't have theta, we've got 4 theta. So, if we multiply the limits here, 0 times 4 is 0, and pi over 2 times 4 would just be 2 pi. So we want all our answers between 0 and 2 pi. I would be using cast for this and the exact value triangles, because from here what I can say is, right, well, tan 4 theta is 1. Let's get rid of the tan, so inverse tan. So tan to the minus 1 of 1 is, and with the exact value triangle from higher, you can see that it's a tan of 45 that gives you 1. So we can say then that, well, we'd be left with 4 theta. So 4 theta is going to equal, and because we just want our answers between 0 and 2 pi, that's just really one cycle with a cast. So tan is a positive, is equal to 1, and tan is going to be positive here and here. So this here for A, this is your exact value answer, which is going to be pi over 4, or your calculator answer. And for T, well, it's going to be 180 degrees plus that, or pi plus that. So it'll be pi plus the pi over 4, which is really 4 pi over 4 plus pi over 4, which is 5 pi over 4. And then from there to get theta, well, we just have to divide every single thing by 4. So theta would equal, well, pi over 4 divided by another 4 would give you pi over 16. 5 pi over 4 divided by another 4 would give you 5 pi over 16. So that there would be your answer. Woo! Example 4, given that w equals cos theta plus I sine theta, show that 1 over w equals cos theta, take away I sine theta. Part B, use de Moivre's theorem to prove that w to the power of k plus w to the power of negative k equals 2 cos k theta. And C, expand w plus w to the negative 1 in brackets to the power of 4 by the binomial theorem, and hence show that cos theta to the power of 4 equals an eighth cos 4 theta plus a half cos 2 theta plus 3/8. So, to start with, we're given that w equals cos theta plus I sine theta, and we have to show that 1 over w equals the cos theta, take away I sine theta. Well, we know that 1 over w, if we move the w to the top line, that's just w to the power of negative 1. So we would have this cos theta plus I sine theta to the power of negative 1. And using de Moivre's theorem for that, well, if you've got a complex number in polar form, if you're working out to the power of something, what you would have is the modulus to that power. So you would have the modulus here, that's just going to be 1, so it's going to be 1 to the power of negative 1, which will stay as 1, so we don't really need to write that. But we have the cos theta plus I sine theta, and we multiply the thetas by that power, so you multiply them by negative 1. So you'd end up with cos negative theta plus I sine negative theta. So that's just using de Moivre's theorem. From there, well, you've got cos of negative theta. But if you think about your cos graph, well, the cos graph is going to start in the clouds and it's going to end up something like this. If you go back the way, well, you can see that it's just going to reflect in that y-axis. So if you have the cos of, say, 30 degrees, that'll be the same as cos of negative 30 degrees. So with the cos of negative theta, you can see that's the exact same as cos theta. With sine, if you're drawing out your sine graph, well, if you draw that out, well, you can see that you end up with something like this. And you could see that the sine of, for example, negative 10 degrees, well, you could get a value for that. But if you work out sine of positive 10 degrees, well, you just end up with the negative of whatever that would be. So you can say that sine of negative theta, for example, negative 30, will be the negative of sine 30. So sine negative theta will just be negative sine theta. With the negative, just bring that to the front, so it becomes take away I sine theta. And that is what we would have. For part B, use de Moivre's theorem to prove w to the power of k plus w to the power of negative k equals 2 cos k theta. So really what we want to do is we've got w to the power of k plus w to the power of negative k, and we know that if we swap w to the power of k, well, it's just going to be the cos theta plus I sine theta to the power of k. And w to the power of negative k, well, we would have for that the cos theta plus I sine theta to the power of negative k. If we work this out to the power of k using de Moivre's theorem, again, this is de Moivre's theorem, so if we've got this in polar form to the power of k, we're going to multiply the modulus to the power of k, but the modulus here is 1. If you do it 1 to the power of anything, it's just 1, it stays. But we'd multiply the argument by k, so we'd have cos k theta plus I sine k theta plus, and then with the cos theta plus I sine theta to the power of negative k, again, it's the same thing. So it'll be the modulus to the power of whatever, but because it's 1 to the power of that, it's just staying as 1. And with the cos theta, well, you multiply the theta by negative k, so it's going to be cos of negative k theta plus I sine negative k theta. With that, the same thing, you're just going to be keeping the cos k theta plus I sine k theta plus, and then cos of negative something is the exact same as the cos of something. So that would stay just as in what I showed you in the graph a minute ago. And the same with the sign of negative something will be the negative of the sine. So you can take the negative to the front. So it'll be negative I sine k theta. With this, what you will notice is that you've got an add I sine k theta and a take away I sine k theta. So they will just cancel out, leaving you with a cos k theta and another cos k theta, meaning you would have two cos k thetas. Woo! Part C, expand w plus w to the power of negative 1 all to the power of 4 by the binomial theorem, and hence show that cos theta to the power of 4 equals an eighth cos 4 theta plus a half cos 2 theta plus 3/8. So using the binomial theorem then, if we've got w plus w to the power of negative 1 to the power of 4, what we can do with that is we can say that that will be, well, because it's to the power of 4, using your Pascal's triangle, you'll have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and then 1, 4, 6, 4, 1. So if you expand that, you will have 1 times the w to the power of 4, the w to the power of negative 1 to the power of 0, which would just be times 1, so we're not writing it. Then we'd have 4 times, or 4, 1, writing it out with the binomial coefficients. So we'd have 4, 1, and then w to the power of 3, and then w to the negative 1 to the power of 1. Then 4, 2, and w to the power of 2, because the power is increasing. The w to the negative 1, that will then be squared. You'd have 4, 3, and the w to the power of 1, because the power again is decreasing. But the w to the negative 1 to the power of 3, because that's increasing. And we're going to finish off with 4, 4, which is just 1, and then w to the negative 1 to the power of 4. That means then you'd have the w to the power of 4 using the Pascal's triangle. I just said you'd have 4 times. That would work out to be w squared. Here this works out to be 6 times, and that would work out to be w to the power of 2 times w to the power of negative 2. Add the indices, w to the power of 0, which is 1, so it's just going to be 6 times 1, which is 6. This here will be 4 times w to the negative 3. Add the indices, so that's w to the negative 2, and that there will be to the power of, so times them together, and then w to the power of negative 4. Where can we go from there? Well, we could say that that would be w to the power of 4, that's what we've got, and we've got a w to the negative 4, perfect, so we've got those two parts. We've got plus 4 times, take out 4 as a common factor, and we'd have w to the power of 2 times add on w to the negative 2, and we've also got this add on 6. We know though from part B that w to the power of k and w to the power of negative k is 2 cos k theta, which means then that w to the power of 4 plus w to the negative 4 will give us 2 times cos 4 theta. We're going to be adding on 4 times w to the power of 2. If we work that out, add on w to the negative 2, well, all we're doing is we're replacing the k with 2. So we'd have 2 cos 2 theta. And we've still got this add on 6. 4 times 2 is 8, so you can just rewrite that. What we have to do next is we have to try and find another way of writing that. So we've got w plus w to the power of negative 1 all to the power of 4. But using this, Well, w to the power of k plus w to the power of negative k is that 2 cos k theta, which means then, well, lots of you might be thinking, right, well, we've got w plus w to the power of negative 1. So really what we're doing is we're just replacing the k with 1, because then that'll be w to the power of 1, and then w to the power of negative 1. So if we replace k with 1, well, that means we'd have 2 cos 1 theta. Or in other words, just 2 cos theta. But because we've got all that to the power of 4, it means we'd have 2 cos theta all to the power of 4. And if we've got all of that to the power of 4, well, it means we've got the 2 to the power of 4, and we'd have the cos theta to the power of 4. And then from there, what we can say is that, well, w plus w to the negative 1 all to the power of 4, we can replace that with 16 cos theta to the power of 4. So we can say that equals just what we found here, the cos 4 theta plus 8 cos 2 theta plus 6. From there, well, we know we want to show that cos theta all to the power of 4 equals, so we need to get down to that, and we do that by divide by 16. Brilliant, divide everything by 16. So we'd have the 2 divided by 16, we'd have the 8 divided by 16, and we'd have that 6 divided by the 16. Simplify that then, it means the cos theta all to the power of 4 would be 1/8 cos 4 theta plus 1/2 cos 2 theta plus 3/8. And that is our answer. Try some of these questions in the Unit 3 booklet on page 67. If you are needing the booklet, send me an email and I will fire it off to you. But good luck with the trig identities. You're wanting to produce them using a combination of the Binomial Theorem as well as the Moivre's Theorem. Yeah. Have fun. See ya. Woo!